Let us now study the Coulomb's law for magnetic forces. About this law, we can state that this law gives the interaction force between two isolated magnetic poles, and here we can say if two magnetic poles of a strengths M1 and M2 are kept at separation R, like this. If there is a pole M1 and there is another pole M2, so if we consider both of these are north poles, they will repel each other, and if they are opposite poles, they will attract each other. However, we know that the unipole cannot be isolated. The pole can never exist independently, but the law is defined for isolated poles, which can be further generalized for bar magnets. We will see later. Right now, we can see the two poles will be repelling each other with a magnetic force if the separation between these two is R. According to the Coulomb's law for magnetic forces, here we can write that the force of repulsion between the poles or force of attraction between two poles is directly proportional to the product of their pole strengths. It is our equation 1, and the force is inversely proportional to the square of separation between the two, which can be taken as equation 2. And combining the two, we can write will include a proportionality constant K, so this will be K M1 M2 by R square. Now this is the expression for Coulomb's law for magnetic poles, and here this K, the proportionality constant, we write as mu by 4 pi, where mu is termed as magnetic permeability of medium in which the magnetic poles are kept. And here just like electric permittivity we have discussed in electrostatic, here magnetic permeability mu can also be further defined as the product of mu naught and mu r, where mu naught is a numerical constant which is 4 pi multiplied by 10 to power minus 7 SI units. Units we'll talk later. And in this situation, this mu naught is called permeability of free space, and here mu r is termed as relative permeability of medium in which the magnetic poles are kept, in which we are analyzing the interaction force. Now in this situation, for free space, we can directly write mu is equals to mu naught, as the relative permeability mu r is taken as 1. In electrostatics, we have discussed that the relative permittivity of a medium is always greater than 1, which is also termed as dielectric constant. But here in analysis of magnetism, we'll see in coming sections and topics that the relative permeability mu r can be less than or more than a unity. It does not necessarily be greater than 1, unlike to the relative permittivity of a medium. Now in this situation, for free space, if we substitute the value of K, the force between two magnetic poles can be given as mu naught upon 4 pi M1 M2 over R square. This is the relation we use for free space. This is the Coulomb's law, which is defined for two isolated poles. In coming sections, we'll discuss about the force applied by bar magnets also.